Welcome everybody. My name's David Keane. I work for Speechmatics. We are a global speech recognition company. I'm going to talk to you a little bit today around some of the work that we're doing on looking at inclusion and diversity within AI, specifically around voice recognition. And we're going to also look at some of the ways that we've been thinking about bias, particularly AI bias and diversity for this technology. Speechmatics' vision and mission is all around understanding every voice, regardless of who that voice is, regardless of where they're from, regardless of their socioeconomic status, etc. And too often AI focuses on wealthy, privileged individuals rather than looking at the entire group of people that we want to include and get the technology working for. And it's interesting when we think about COVID-19 and the process that we've all just been through, where everybody moved online, regardless of who you were or where you were having to do many things online. So this technology has to work for everybody. We can't exclude people. Speech recognition as a basic problem is not solved. We all think that our phones are fantastic and we can use Siri or Google or Alexa and do simple command-based recognition. These things don't work particularly well. There's lots of challenges with them. And when we start to look at long-form speech recognition, it gets even harder, particularly where there's a conversation going on, where you've got multiple people talking together. And I'd encourage you to all come across to our booth in the hall and have a look at the technology we've got running live there and how it works with long-form interactive conversations where you can genuinely transcript and look at the words that are being said by a range of individuals. So this is a tough problem. The problem is not solved, and it's not solved as well for a wide range of different diverse users. So when we have people from less privileged backgrounds, when we have people with different accents who come from different locations or communities, then we find that actually these technologies don't work as well as they should do. So we've been building technology to actually recognize different diverse groups of people. And I just wanted to define some of these terms before we go in here for diversity, equity, and inclusion. So diversity is all the ways that people differ. So in this instance, we're thinking about the taxonomy that we apply to AI around where do people come from? What communities are they part of? How do they speak? What accent do they have? Do they have a disability in the way that they speak? Or do they have some kind of other way of pronouncing things? Do they have a background that influences the choice of words that they might use from their family environment, etc.? So diverse speakers are really, really key, rather than just thinking about the narrow set of speakers that we typically train models on. Inclusion is then really making sure that this works for everybody, rather than just the privileged set of people that we will typically test these technologies on themselves. And equity really is about thinking about how does everybody get fair treatment. And when we're measuring different levels of accuracy with these technologies, how do we measure this in an equitable way? And I'm going to share some ideas around that. So where do we start in terms of accuracy for speech recognition? So the standard measure is word error rate in the speech industry. And when we're looking at word error rate, we're looking really at the total number of words. And then we're thinking about the substitutions, the deletions, and the insertions that we need to do to get to a perfect transcription of some speech. And that kind of gives you a percentage error rating accuracy. And typically what people will do, they'll talk about the accuracy of a particular engine for a particular cohort, and they'll take that number away from 100. And when we look, these are some accuracy comparisons that we've got here around the Speechmatics speech engine and other hyperscaler engines, obviously Google, Microsoft, and cloud provider A, who we can't name for contractual reasons. So a range of different cloud vendors out there. And what we can see is there's a range of different accuracy values. Now, when we look at these accuracies, this is the test data set of labeled data that we've got, running it through each of these platforms. As an industry, we don't have a single agreed set of test set data that we use in these environments. So this is quite a narrow set of data that we're working with here to get these different levels of accuracy around word error rate. In terms of the work that we've been doing at Speechmatics, though, we've been starting to think about how do we widen that out. So instead of saying, let's take a labeled data set of data from a newsreader, for example, and run them through the engine and use that as the measure, we're starting to look at how do we look at people from different cohorts. And this concept of voice cohorts is working really strongly for us right now. So thinking about age, gender, what kind of community does the person come from? What location are they based in? How do they speak? So thinking about all of those things as we measure them and trying to widen out the accuracy measurements that we've got. I'm going to talk you through a little bit around the journey itself of tackling bias in AI and tackling bias in the society that sits behind all of this data itself. So, moving beyond word error rate, why are we doing this? We're doing this because there's been this explosion of unstructured data that is full of speech. And that speech is massively valuable to all of us, and particularly to business. So taking value from all of that speech is really, really important. And that speech itself and all of that unstructured data is coming from social media, it's coming from a range of different platforms, all of the meetings that we're now having being online. We've got this whole COVID-19 working from home and this new normal environment that's changing the way this data is generated. And then we've got changing patterns of use. You know, many of you who are lucky enough to have children, will know that your kids probably consume data in a completely different way, often with subtitles on, so that they can actually do multiple things at the same time. And then we have a range of other parameters in here around diversity, equity, and inclusion that allows us to think about gender, thinking about inclusion, thinking about race and location and community that people are part of, and thinking about the socio-demographic backgrounds of people. People based on their privilege often speak in very different ways due to the community that they're in and also due to kind of the level of education and engagement that they've had with different ways of speaking. So these are the things that are driving the work that we're doing. The other things that are driving this is legislation. Now, obviously, we're in the US right now. We did this talk in London a little while back. And one of the things that's happening in the European Union right now is a set of legislation around AI bias that's starting to come down. So you will have seen a lot of data protection legislation, GDPR, et cetera, the Californian equivalent of it. There's going to be a whole range of legislation around AI bias and specifically looking at the test data sets that people use and how bias is then measured. So this is really, really critical moving forward, that we start to think and engage with these legislative initiatives. So when we think about bias, when we think about how bias comes to pass, we think really about starting from selection bias. So a typical way that we'll build models is we'll take labeled data. Now that might come from data that we have from different test data sets that we've built ourselves, or that have been provided through our customers, or that have come from audiobooks, for example, and they will have a subset of voices in them. If you take audiobooks as a really great example, can we do a show of hands? How many people here have ever produced a full audiobook themselves? Anyone? No? Okay, so no one in this room has ever produced an audiobook. If an audiobook is a key way that we train the models that sit behind speech, then none of your voices are being recognized in that model training. So by getting more and more voices in there and finding a wider and wider data set, we can start to build technologies that can actually recognize all voices rather than just the limited number of voices that this selection bias starts to bring out. And if we look here at the data that we've got around this particular open data set, and we have a look here, you'll see that in this particular data set here, we've got 71,000 hours and 12,000 books in English. Fantastic. We've then got 3,000 books in German, 2,000 books in Dutch. If you're Italian, there's only 279 voices going on in there. So when we look across all of the languages and just recognize that actually this technology has to work not just for global English, but for every language that we have on the planet simultaneously, then it's really, really key that we're looking at applying equal sets of data there. Equally, if you look on the right here at the kind of male-female split, what we'll see is that the training data for English is pretty good. Once you get down to Dutch, we've got 9 male voices and 31 female voices. So that model is going to be far better for female voices, but still there's only 40 people that are training that model out of an entire population on the planet of people who speak Dutch, which is in the many, many millions. So you'll see that there's a lot of bias coming here in terms of these small number of voices training and building models to then start to deliver these technologies for speech recognition. And this brings us on to this idea of voice communities. So when we think about a standardized bell curve of accuracy, then when we're looking at word error rate, we're typically looking at this line between the second quadrant and the third quadrant, the line between the blue and the yellow there. So whenever you're talking to a speech engine company or hyperscaler, et cetera, and they're talking about accuracy, they're describing that line there at the top of the bell curve. The dialogue we would like to encourage in the industry is how do we change the shape of that bell curve? Because when you've got the pure newsreader, CNBC kind of person, you can recognize their speech very easily. When you're looking at society, you see the curve dropping off on the sides, and it doesn't recognize it in the same way. So this bell curve needs to widen. So we need both that narrow accuracy and we need wide accuracy across many different voice cohorts. So how are we going to achieve all of that? And what is the work that we've been doing as Speechmatics? So we've been working particularly with Stanford here in the Bay Area around a lot of the work that they've been doing around African-American voices and looking at the accuracy of AI technologies around those communities. And building out this technology for recognizing speech, what we've done is start to think about age, gender, race, and all of the different accents that go with that. And then starting to use different mechanisms for creating and building training data to start to build language models and building acoustic models that can both recognize the different cohorts we're working with and that can take noise out of the whole piece. And the use cases that we're looking at here are a range of different use cases. So transcription, so interpreting, recognition and monitoring and pulling out metadata, analytics and understanding, control and driving systems. So if you think about, McDonald's would be a good example. If you go through a McDonald's drive-through and you have speech recognition looking at what you're ordering, that speech recognition should work for everybody on the planet. Everybody who might go through and purchase some kind of food product or beverage product there from McDonald's. So we need to have this stuff working consistently and effectively for everybody across all of these use cases. And explaining speech recognition and how this works in the old world and where we're taking it in the new world, we can look here at this idea of somebody says something, noise is then stripped out, features are then pulled out of that speech, and it's then passed down to an acoustic model to recognize phonetic structure and phonemes and assemble them into words. And then that is mapped against a language model so that we understand the speech that's in there. So this is the old way of the world. And what we would build would be, we'd build an acoustic model based on labeled data and a language model based on kind of internet word structures that we have out there where we're saying, for these 10 words, what's the next likely word for word number 11? So this is the old way that we used to build this technology, and we've invented a new way of doing this using self-supervised learning to start to get a much bigger data set that is completely unlabeled. So what do we call this? We call this autonomous speech recognition, and this is the move from this old automatic way of thinking about it with this simple acoustic model and language model where we pull the two together to one where we actually do a whole bunch of pre-training before it gets down to those end models there. So this self-learning on the internet allows us to go out and start to look at different internet data sources and particularly look at the phonetic structures inside things like internet radio, podcasts, TED Talks, the things that are out there that we can go and have a look at without any concern for copyright or any of those things. So we can look at that data, we can then build a very, very large data set of phonetic structures, and we can start then to recognize much wider communities and cohorts. So how does this work? Well, how it works is we build and we train a whole bunch of models using self-supervised learning looking in an unsupervised way at the internet as a whole to build those language structures. We then configure the engines that we've got, and our engines deploy on many different platforms, SaaS, private cloud, on device, etc. That then gets deployed, and then that runs in real time, and then engages and actually does all of this transcription, running point-of-sale systems, pulling out metadata and analytics, etc. So this is the kind of background structure that's working here. And we're thinking about, for example, how often do these models get rebuilt? As new words come through, how often do they come in? And can we move towards more synchronous updates of these models? And building these models at that first training stage in our new technology, this autonomous speech recognition, is working in this way. We're looking at broad internet audio, and we're pulling out all of the different phonemes for as many sources as we can, moving to millions of hours of audio where we're pulling out every phonetic structure that we can find there for men, for women, for young people, for older people, for people from different backgrounds, etc. So getting this big data set, pulling many, many phonetic structures out where those structures are labeled by the self-supervised learning. We then use a small amount of labeled data to actually connect that back to the language models that we're building. Okay, so we're building these big language models across all different languages. Then we're using this unsupervised learning, using self-supervised techniques to go out and look at the internet and build massive structures around the phonetic models that are out there. And this is what's giving us this huge lift. And when we run this at runtime, we have the whole idea of a first layer model that's doing pre-training on the inputs that we've got going in there, that's actually thinking in a human-centered way. So it's coordination of that input. It's figuring out the acoustic structures that are in there before it's passed to the model. It's taking noise out. It's rebasing pitch. It's doing all of those kind of things. It's then being passed to the acoustic and language model, and we're looking at how they can be adapted, how we can put specialist words in there, how we can figure out who is saying what the language is that's being spoken, and then how we post-process all of this for profanity, for numbers, for monetary values, doing all of those kind of things that we would take out of any kind of speech that somebody says to make it more realistic on the page in the written word. So this is the self-supervised learning model that we're now operating. And if you come and test our technology, which we'd love to give you access to, you'll actually get to use some of these immensely large models. So training the future, how do we build this and what's the results that we're getting? I want to kind of share some results with you from the work that we're doing. So this is the accuracy between adults' voices and children's voices. And I'd just like to say on this, we've not gone out and scraped children's data from the internet, as somebody asked me the other day. We've just gone out and pulled data sources from places like internet radio, etc., where we can pull very large phonetic structures, and it then gets applied automatically across these. So what we're seeing as we look at the different vendors that are out there selling these technologies, there's different levels of accuracy based on under 18s versus above 18s. And what we're finding is this self-supervised model is giving us a big uplift in accuracy as we move to this. So it's not just giving us better accuracy across languages, across all languages, it's giving us better accuracy across these age ranges. We then also, using the African American data sets that Stanford have been putting together, we get a huge uplift in African American voices recognition. So literally, when you look at all of the other vendors that are out there, their accuracy drops by 10 to 20 points based on an African American voice. And what we're finding is by listening to the internet and doing that self-supervised learning, we're picking up the phonetic structures, and we're able then to give equity to the African American voice, voices from other communities and other locations, other accents. So we've been doing a whole bunch of testing around like Celtic accents from Ireland, Wales, Scotland, etc. Accents of people who are speaking French in Switzerland using very different tonality. People in India speaking English and actually recognizing their voices. We're seeing huge uplifts based on this kind of much, much larger acoustic model that we've been building here. So my final kind of call to action for you, and then I'll take a few questions, is come to our booth. 556. There's a QR code there. Everyone take a picture of it, and you can download access to the full engine for a month. The QR code is also on our stand if you want to come across and talk to us, and we can also demonstrate all of these technologies for you. So thank you so much for being here. Thank you for listening.